Hey everyone and welcome back to PrepFusion. So today we'll start the lecture 2 of power semiconductor devices, okay, of the chapter 1, that is. Just hold on, lecture 2 of power semiconductor devices. So in this lecture we'll study about transistor family. We'll study about mainly 3 devices. First one is the power BJT, second one is the power MOSFET, and third one is the power IGBT. So we'll mainly study theoretical points in this lecture, so listen to me carefully here. So we'll not do any numericals here, we'll just study theoretical points, because sometimes theoretical points also come in the gate examination, and also this is important regarding the ESC examinations also, okay. So one thing I want to tell you is that before starting this lecture, it's better to go through your BJT notes. So just go through the construction of BJT and how does a BJT work, okay, the theoretical part, not the circuit analysis part, just the first portion of theoretical part. Also I will try to add a video which will explain you the working of BJT, not the circuit analysis, just the working of BJT, right? So that is important. I will put the links of the video of Himanshu if he has taught that in the analog electronics course. So before starting, I gave you a few homeworks through the previous lectures. So this question, right, I just modified this question a bit, else this question would have been incomplete. So we have to find the reverse recovery time of a diode is given, TRR equals to 5 microseconds, and the rate at which the diode current is decreasing is 5 ampere per microsecond. This is the decrease of the current, rate at the decrease of the current. The reverse recovery charge QRR and the peak inverse current IRR of the diode will be if the softness factor is very less than 1. So if the softness factor is very less than 1, right, so we know one thing, that if the softness factor is very less than 1, then our reverse recovery charge is almost equals to this, right, half into di by dt into TRR whole square. So they have given us di by dt and they have given us TRR as well, so we can easily find out. So like these type of question can come in ESC, because there they will not mention what is softness factor. They will directly write that softness factor is very less than 1. They will not mention what is softness factor, so you have to know that. So these type of question can come in ESC. In gate it has very low probability to come. So if softness factor is very low, S is very less than 1, right, so QRR equals to 1 by 2 di by dt, okay, this is equals to TRR whole square. So this will be what? This will be half into di by dt is 5 by ampere per microsecond into TR whole square. So what will happen? Microsecond whole square will happen, right? So this will be in microcoulombs. So this will be 2.5 into 25, which is 62.5 microcoulombs. Now what is the maximum current? Now what if you notice here, right? If you notice that if your softness factor is almost very less than 1, so your T4 is TRR, and what is your IRM? IRM is equals to di by dt in T4, which we derived earlier, right? So basically IRM is equals to di by dt into IRR. So if S is very less than 1, right? So our IRM will almost be equals to di by dt into TRR. So this is equals to 5 ampere per microsecond into TRR, which is 5. So this will be 25 amperes. So maximum peak current, right, will be 25 amperes. That will be the answer of this question. So let's go to so in this question they are asking which of the following statements about Schottky diodes are false. So first statement is Schottky diodes do not store charges, which is true. That's why it is the fastest, right? Here the reverse recovery time is in nanoseconds, and here I have told you it has a metal junction, it does not store any charges. That's why it is the fastest. So this statement is true, so hence it is not our answer. The main charge carriers in a Schottky diodes are holes. This is false, right? Why? Because I have told you it uses typically n-type silicons. So n-type has electron as its charge carriers. So this is a false statement, so this will be true. Like this answer will not true. This will be our answer. Next, let's read this. Silicon diodes have an aluminum silicon junction. Schottky diodes have an aluminum silicon junction, which is true, right? Because we have studied that it has a metal junction, and which is true. So Schottky, this is true, so hence this can't be false. Schottky diodes can be switched off more quickly than similarly rated PN junctions diodes. So this is again true, right? This has the lowest reverse recovery time. So this is true statement. Okay, hence this will also not be my answer. My answer will be B in this case. So let's go to the next question. So the next question is, the Schottky diode is utilized in high speed operations due to small current potential. Is this true? Small current potential, I don't know what is it talking about. Minimal storage delay, this can be true, right? This can be true. Now small size, we need to small size I'm using it. No. Now high speed of electrons, but high speed of electrons is also present in normal p-n junction diodes as well, right? Why Schottky diode? Because it has no storage delay. It does not store any charges because the junction itself is made of metal. Its depletion width is 0. Okay, so hence option B will be correct here as well, because it has minimum storage delay. Electrons, they are charge carrier everywhere, so speed is same everywhere, not just like in this particular case the speed of electrons will be higher than the speed of electrons in the normal p-n junction diodes. That won't be the case, right? So charge carriers are used as electrons in other devices as well. Okay, so that won't be the case. This will be the answer of this question. So like these were the few theoretical points that I wanted to address. Now let's basically start with our lecture 2, that is transistor family. So first member of our transistor family is power BJT. So if you have studied already BJT, you know that BJT has a construction like this, NPN or PNP, right? It has two junctions, this, right? Base, collector base junction and emitter base junction. So like working, I hope you have studied from Himanshu. There he has explained the working and thing. Symbol is this, and power BJT also has same symbol and same construction with a difference. What is the difference? Again, we introduce a drift layer over here. We introduce a drift layer. This is a drift layer, right? We introduce an intrinsic layer. Why is this intrinsic layer introduced? This is introduced because to handle large amount of reverse voltage under breakdown condition. Same reason as power diode. We introduce a drift layer to handle the reverse voltage. So this has lesser amount of charge carriers. Hence this can also the depletion width is larger. Okay, longer. Hence we can block large amount of voltages. Okay. And why is this doped highly? This is doped highly. These two are doped highly to support large amount of current, right? Supports large amount of current, not reverse voltage, support large amount of current. Because when it is forward bias, large current will flow and these will provide us the charge carriers for those current to flow. So these are highly doped and this is lightly doped and this is moderately doped. So just similar like power diode only, just here we have a extra junction. So there is two junction. There are two junctions. So why there are two junctions, we'll understand that. Okay, we'll just go through a bit about this. So let's read few key points. So what are the key points? In power electronics, we use NPN instead of PNP as mobility of electrons is faster than holes. So that's the reason to use NPN, not PNP. In BJT, conduction due to both electrons and holes occur. Hence it is called a bipolar device. So it can also block voltage in both directions. That is also another reason. And another reason is it can like flow of both the flow of current happens due to both electrons and holes. That's why it is called a bipolar. So this bipolar has a bit of confusion per se. So don't get confused. Your first option should be, can it block both side voltage or not? If it cannot, so you will say it is unipolar. But in worst case, what may happen is they may ask about this also as well, that if both electrons and holes flow, then also you can call it as bipolar. Okay, so that is also another definition for bipolar. Now it is a majority charge carrier device. It is a minority charge carrier device, as like both electrons and holes are flowing. There is no one majority charge carrier, right? That's why it is a minority charge carrier device. Cross sectional area of BJT is more than normal BJT. Power BJT is more than normal BJT to increase the current rating of the device. Hence device is made vertical. Like this is a theoretical point. I hope you understand. Power BJT will always be designed by NPN because of the mobility of electrons is faster than holes. Okay, this is again like repeated, so this point doesn't need to be here. To block high voltage, we need one intrinsic layer, that is the drift layer in BJT. And hence power BJT has 4 layers. Like in normal BJT we have 3 layers, PNP and NPN, but power BJT has 4 layers. That is the difference between normal BJT and power BJT, right? So this is an important point. So you will see most cases, right? We'll just make a slight modification in the construction and we'll make the device suitable for power electronics applications. So let's go on to the next slide. So next slide is telling that high collector doping increases the charge carriers and device connectivity. So obviously in forward bias, more current needs to flow hence like for not forward bias, when the device is in conduction, I want more current to flow. That's why I provide high collector doping to support that more charge carries and more conductivity. Conductivity modulation of the drift layer occurs similarly to power diode, reducing conduction losses. So the same conductivity modulation phenomena happens here. The collector and the emitter serve as power terminals. The collector and emitter serve as power terminals, while the base is a control terminal. Why is these two are called power terminals? Because in collector and emitter I give the input, okay, and with the help of base current I can control the on and off of the BJT. I can turn on the BJT or turn off the BJT. We'll see just in a brief about the working of power BJT, and there we'll understand this. Okay, so in this case what is happening? So here what you observe is our VC is less than 0. So like I have assumed the terminals like this. Just what I will say, I will just say a intuitive analysis here. I will not say the exact analysis. For exact analysis you can go through the books and refer to those things. Those are not important here. So the simple analysis is this plus terminal is connected with this N, and this minus terminal, like I can bypass this, is connected with this N, right? So what is happening? This plus is connected with N anyway, so this junction will be reverse bias. Whenever a positive terminal is connected in the N channel, right, it is reverse bias. So this JEB is reverse bias because plus is connected with N, and this minus, if I go through here, minus is connected with P. So that's why, right? Now the next point comes for this JCB junction. So this plus is connected with this P, right? Also P, okay? This plus is connected, like P, I don't know what P is connected because this base is floating, okay? There is no base current, base is floating. Now this negative is connected here, okay? And this positive is connected in this emitter, and that will be somewhat here as well. So what will happen is that this junction will be forward bias as this negative is connected here, okay? So that will be forward bias. So junction JCB is forward bias and junction EB is reverse bias. Emitter based junction is reverse bias, collector based junction is forward bias. You can go through the BJT analysis of Himanshu, he will also explain that. Now if junction JEB can't block high voltage due to N plus, so it has N plus, right? So junction JEB, like not this one, it has N plus. So junction EB has N plus, so obviously the width of the depletion layer won't be very high, okay? That's why it will be low. So that's why it cannot block very high amount of voltage even though it is reverse bias. So range can be 10 to 20 volts, okay? Now current cannot flow from emitter to collector without damaging the device. So if we apply a voltage higher than the breakdown voltage of this emitter based junction, then only current can flow, else it cannot flow, because even though the collector based junction is forward bias, right? Even though the collector base junction is forward bias, because this negative is connected to this N and this positive is connected to this P, but this is reverse bias, right? So current cannot flow. So current has to flow from here only. So current cannot flow because it has no path. So one junction is reversed biased. Okay. So let's go to the next case. So in the next case, a interesting thing is happening. We are making our VCE for like positive, right? We're making our VCE positive. So if we make our VCE positive, what will happen? So in this case, right, I am applying this as positive and this as negative. So quite the opposite thing is happening. What is happening is that again, plus is connected to this N and negative is connected to this N. So this is reverse bias, right? So what is happening? This junction, this JCB junction, right? This plus is connected here. So this JCB will be reverse bias and negative is connected with this and positive is connected with this. So this JEB will be forward bias. Just I am doing with the anode and cathode thing. Okay. Just for the analysis part, I will not explain the internal things here. Okay. That is not that important for gate purpose. So I'm just explaining you intuitively what is happening, how to understand. Now junction JCB is capable to block high voltage. So I should write to block. Junction JCB is capable to block high voltage due to N minus. As N minus is present, right? Drift layer is present. So obviously the R1 is very high. So it is capable of blocking high voltage. The reasons I have explained in the previous lecture of the power diode. Now what is happening is that hence BJT can block high positive voltage. So like one junction is reverse bias, so hence it can block high positive voltage and it can block negative voltage as well, but not to that high extent, So in the next case, what is happening is that what is happening in this case, right? Base current was 0, base current was floating, this was also floating. Now what is happening? I apply some voltage at the base and some base current flows, right? IB current flows. Now if IB current flows, what will happen is that the reverse bias junction JCB will become forward bias due to the excess charge carriers present here, this will like make the depletion width to 0 and the charge carriers will flow. And once the charge carriers start to flow, right, this will become forward bias, and this was already forward bias, so this charge carriers will also flow, this charge carriers will also flow, and as this charge carriers also flows, the device turns on, because this was my power terminals, right, this is the control terminal, this was the power terminal. Okay, so this current also starts to flow. So basically we require base current to make junction JAB forward bias. So this junction was previously sorry, not JAB, JCB, right? As you can see, this just hold on. Yeah, this junction JAB JCB was reverse bias here, like plus is connected here and minus is connected here. So this JCB was reverse bias, but as the base current flows, right, base current flows, this gives us excess charge carriers. With the help of those, this JCB junction becomes forward bias, depletion width becomes 0. So depletion width becomes 0 and more current flows, and which turns on the BJT. So BJT is on in this case, BJT is on. In this case BJT was off. So IC is that's why IC is called, the IB is called the control terminal, because with the help of base current I can control the on and off of the BJT. Okay, it doesn't matter what is the voltage here, if some base current flows, it turns on the BJT. Now what is written over here? So what happens is that when the base current flows and huge number of base current flows, local hotspots happen right here. So basically excess charge carriers are present over here, because already what was happening is that my VCE was positive, so this was positive, this was positive and this was negative, right? So here huge number of electrons were present here and huge number of holes were present here. So as soon as the current flows, right, current direction is this, so if current direction is this, electron direction will be this, so huge number of electrons will start to flow from here to here, right, huge number of electrons will go. So because there was huge number of electrons here, so here local hotspot will happen of holes and electrons. So if local hotspot happens, the number of electrons is very high. If the number of electrons is very high and they will like strike with each other, right, they will generate heat. They will generate heat because here there are very huge number of electrons that are colliding with each other. So there is a very high amount of heat, and due to collision, the heat, like the power loss is due to heat. What is happening? The temperature is increasing, and as the temperature increases, more and more electrons collide, because the kinetic energy increases of each of the electrons and they collide with each other. Okay, and this is a loop, right? Again, more and more electrons collide, more and more heat loss there is, so the temperature increases, and this is a loop. Temperature increase, more electrons collide, heat increases, temperature increase. More electrons collide, heat increase, temperature increase. So this is called as the secondary breakdown problem. So basically this is also known as the forgot the name, thermal runaway. This is also called as a thermal runaway, that I hope you have studied. So secondary breakdown problem, what is a secondary breakdown problem? As temperature increases, the reverse saturation current of the collector base junction increases. Okay, so the current will increase, the number of electrons will increase, the number of electrons increases, the collisions will increase, more they collide. Okay, and the more temperature will increase. So here specifically the reverse saturation current ICBO doubles for every 10 degree rise. Temperature increase, 10 degree rise, ICBO doubles. Now continuous temperature rise can cause thermal runaway or secondary breakdown problem. Thermal runaway occurs when the increase in IC due to temperature rise leads to further heating, creating a feedback loop that can thermally damage the device. What do I mean? So first of all, I told you, right, due to collision of electrons, the temperature is increasing. Now if the temperature increases, I've already mentioned the reverse saturation current ICBO increases, right? ICBO increases. Now if the ICBO increases, what happens? The IC increases. Now if the collector current increases, the temperature will again increase as more heat is getting generated. Okay, more heat is getting generated. So as IC increases, temperature more increases, and again as temperature increases, ICBO will increase, and this will go on a loop, right? This will go on a loop and we cannot control it. So we need a cooling device. So that is the drawback of BJT, power BJT. That's why we don't use power BJT now, except few circuits. BJT has no use currently. So case 4 is what? VCE is positive and IB is not equals to 0, but I am trying to turn it off. I am making IB equals to 0. Can I turn off the device? Can I turn off the device? And the answer is yes. If IB is made to 0, from not equal to 0, if I make IB 0, the BJT will be turned off. So this is a fully controlled device. BJT will be turned off if the base current is removed. After removal of the base current, recombination takes place and BJT will turn off. Again, the depletion width will increase and decombination will take place. So the main flow was due to this IB, right? IB. So we can turn off the BJT faster by introducing a negative base current by small duration. So obviously there will be some reverse recovery charge if I apply negative current, right? So the reverse recovery charge will be depleted faster, okay, if I apply a negative base current. So all these things are theoretical points you should know. So what is the IV characteristics of a BJT? So IV characteristics of a BJT, if you have already studied the PU quizzes, you will know. So this is with respect to IC and VC, the IV characteristics are something like this, and this is the this looks like a diode, right? Characteristics similar to diode because we mainly have a PN junction diode. And for an ideal BJT, right, it should be like when it is on, it should be on the y-axis, that is IC can be any value, and when it is off, right, it should be able to block any forward voltage. So but it only can block a very small amount of reverse voltage, right? But still I haven't shown it here, but it can block a reverse voltage as well, right? So these are the characteristics that you should know. Okay, now what is the difference between analog and power BJT? Power BJTs have higher breakdown voltage, I told you, due to reduced layer, and higher current rating due to their vertical structure, and obviously higher doping has been implemented here to the N region. Power BJTs operate in cutoff and saturation region, while analog BJTs function in active region for amplification. Even though we don't use BJTs now for amplification, just to save the differences. Now, why cutoff and saturation? Basically, in cutoff and saturation, it can either be on or off. So basically, we use BJT in power electronics as a switch. Right? We use in power electronics as a switch, nothing else. So here a few key points are written about power BJT. So theoretical points may come. It is a 2-junction JEB and JCB, 3-terminal base collector emitter 4-layer device. It is a unidirectional device. Current can flow in one direction only. It cannot flow in the opposite direction. It is a current control device because I am controlling the base current. With the help of base current, I can control the conduction of the device. Higher leakage current as minority. It is a minority charge carrier device, right? Because both electron and hole support the flow of current. So there is higher leakage current as it is a minority charge carrier device. Its switching frequency is low. Why? Because it is a minority charge carrier device. Because there is a storage of charge as well, right? There is a PN junction. That's why. Now, it can block positive voltage. I've already mentioned this. It is a fully controlled device and comes into the category of active devices because obviously we have to provide a supply as well. Just hold on. We have to provide a base current. So the base current comes from a supply. So that's why this is an active device. Power BJT is either operated in cutoff or saturation mode, but not in active mode. I was already explained here. Okay. So these are the few key points about power BJT. Now we'll study about the power MOSFET. So like power MOSFET is just almost same as normal MOSFET, but there is a bit of difference in the construction. Again, there is a N- region which helps in the drift purpose, right? Which gives the drift layer and which helps in blocking higher forward voltages. So also we have to take care of a diode, body diode as well, which you haven't studied in the MOS physics. So there, I don't think he has mentioned about body diode. He must have told you about body diode just in brief, but not to a higher extent. So we will study about this as well here. So I hope you have watched the MOS physics lecture, then only you are watching this. So I will not explain too much into details about the construction and working of different regions and the VI characteristics that has been explained in the MOS physics lecture. So what is the construction? So basically we use N-channel enhancement power MOSFET as it has better mobility. For the same reasons as like electrons will flow and it has better mobility, better conduction, better conductivity. Hence we use N-channel power MOSFET. Drain and source terminal are known as power terminals. Gate as control terminal. So this can be in a single line itself. Okay. Now, oxide layer is kept below gate terminal to minimize current flow to gate. Current flow to gate to the device. From gate. It should be from the gate terminal. So basically, like we place a oxide layer just below this gate terminal. This is the oxide layer, right? Si2O layer. So this is the Si2O layer. SiO2 layer, which we place to totally isolate this gate from this source terminal, right? Source layer, so that no current flows through this, no leakage current is there, so gate current is always 0. It is a voltage control device. As gate current is 0, right? It is isolated with SiO2 layer, so gate current is 0 anyways. Hence we control through gate voltage. Like if we apply a voltage over here, a electric field is generated, and obviously charges like electrons and holes are getting attracted here, and there is a path for current flow. So that we will understand. That I hope you understood in the MOS physics part. So it is a unipolar device, as current flows due to either holes or electrons, not both, right? The current can flow either due to hole or electron, not both. Also we cannot like exactly block a reverse voltage, right, with this, because there is a body diode, so we cannot block a reverse voltage, but we can block a forward voltage. We'll understand about that just in a bit. Okay, so it is a majority charge carrier device. Because why? Because only it is unipolar. As it is unipolar, only current conduction is due to either holes or electrons, not both, right? So only one charge carrier is present, that's why that charge carrier must be majority. So that is the majority charge carrier device. It is majority charge carrier device. So let's understand different regions. So in the first region, right, again we have here two junctions. This is a junction J1 and this is a junction J2. This N and P, N plus P plus, and this P plus N minus. So junction J1 is reversed bias if my VDS is negative. So if VDS is negative, what does it mean? So basically, if VDS is negative, that means drain is VDS is negative, drain is negative, okay, and source is at higher potential, so source is positive. So if source is positive, again plus is connected with N plus and minus is connected with P plus, so obviously this J1 junction will be reverse bias. But if this plus is connected with P plus and this minus is connected with N minus, so this will be forward bias. This is just a way to intuitively understand this. This is not a perfect way, but I don't have the time to explain all the internal things right here, because we don't need that anyways. We just have to do the circuit analysis. That is not required in your exam. Don't worry, this is analysis is not required at all. Okay, that's why I'm skipping this right now. So like this J1 junction is reverse bias, J2 is forward bias. So one junction is reverse bias, right? So hence no current will flow basically, and in this case, right, we don't apply any gate voltage. We don't apply any gate voltage in this case. So but one thing is, junction J1 is reverse bias, but it cannot block high voltage due to its high doping, right? Due to P plus and N plus region, due to high doping, the depletion width will be lower, and obviously it cannot block high reverse voltages. Now as VSD is greater than 0, body diode will turn on. Okay, so what is happening is that there is a body diode in the MOSFET that I will explain in the next slide. Like that diode is formed between this P plus and this N plus, right? That body diode is formed between this P plus and N plus. So obviously what will happen? Now VSD is greater than 0. So VDS is less than 0, but VSD is greater than 0. So this junction is forward biased, right? So some leakage current will flow through this. Current will flow from the source to drain without triggering. So some amount of current will flow if I apply enough voltage to forward bias this body diode. So body diode is present, something like this, right? This is the body diode. So it is formed between the body and the drift layer. But since body is shorted to source, it can carry current from source to drain. So basically this is the body. This is our body, right? And body in generally what happens is, if you have studied MOS physics, it is sorted with the source terminal as well, right? Body is sorted with the source terminal. So what is happening? Source and body are same. So this potential is here. This is some what we are providing. We are providing some positive potential here, right? Some positive potential, and this is some negative potential. So this body diode, right? This is positive, this is negative. If I apply enough VDS, this body diode will turn on. Okay, will be forward bias and current will flow. Okay, so this is the body diode. Basically understand, this junction is the body diode. Current during normal operation flows from drain to source. So our normal operation current is only when the current flows from drain to source and not from source to drain. If some current is flowing from source to drain, that means the body diode of the MOSFET is active, and we definitely don't want that. Okay, that has happened due to some other reasons. We didn't like, that was not under our control, right? That was not under our control. We don't want the current to flow through this body diode. That is uncontrolled manner of current flow that we don't want. hence it is called a bi-directional switch, because MOSFET can allow current in both directions, because due to this body diode, right, it can allow from source to drain as well and from drain to source as well. Okay, so even though we don't want that, but it can allow current in both directions. And this source to drain, right, this is not under our control, because gate is our control terminal and we haven't done anything with the gate terminal yet. So without doing anything, without doing any control, it is automatically letting current to flow, which we don't want, obviously. So it is uncontrolled manner of current flow. But as current is flowing in the opposite direction, source to drain, so what we can say is it is bidirectional, because current generally flows from drain to source, but source to drain also current can flow due to this body diode. Now if VDS is greater than 0, so VDS is greater than 0, that means my drain is positive, again source is negative. Now if as this source is negative, so negative is connected with N plus and positive is connected with, basically, like if I ignore this for a second, with P, right? So this junction J1 will become forward bias, but positive is connected with N plus here and negative is connected with this P plus here as well. So like this, I'm talking about this junction now. And so this junction is reverse bias. Yeah, this junction J2 is reverse bias, but this junction J1 is forward bias. Just I have explained with intuition, nothing else, right? So now what is happening here is junction J2 is capable to block high voltage, as it is a intrinsic layer due to the drift layer, right? Block high, capable to block high voltage. It's capable, this should be block, right? To block. Okay, hence MOSFET can block high positive voltages. Okay, although it cannot block too much of a high reverse voltage, because body diode will get turned on and it will flow current, but it can block high positive voltages. Okay, next let's go to the case 3. Now this time, right, I am applying something in the gate terminal. So VDS is positive. So if VDS is positive, again drain is plus minus minus, source is minus, and this is again VGS is positive, so gate will be positive. So now gate is positive. So what is happening here is that, like this Himanshu also explained, I hope I know he has explained. So here basically again this junction is J1 is also getting forward bias and J2 is also getting forward bias. How? Due to this gate, right? Due to this gate, what is happening here, right? Many electrons are getting attracted. There is some positive electric field, right? So many electrons will get attracted and a channel will be formed. And due to this channel, right, so current can, like these, due to this negative, right, these electrons are getting repelled from here, so a channel of electrons will get formed, and here I have positive, right? So what will happen, enough electrons will get formed here so that this can break through this drift layer and all the electrons can go to this positive terminal, because they are attracted to positive. So like just I'm explaining intuitively here, so there will be flow of huge number of electrons and the device will turn on, basically due to this channel. So basically positive voltage is applied to the gate terminal, the electric field passes through the oxide into the device. Okay, due to the electric field no current flows, but we generate an electric field, and due to that electric field these electrons are present over here, and due to this huge number of electrons a channel is formed. Okay, this electric field exerts a force on the holes and electrons inside the body. Holes are pushed downwards. Okay, sorry, this holes are pushed in the opposite direction and electrons are pulled upwards. So these electrons are pulled upwards, and this, due to this electrons a channel is formed, basically, right? So yeah, that is the case. And like electrons accumulate below the gate terminal while holes are pushed away. As I explained, a small region between the gate has more electrons than holes, behaving as a n-type region. So this region, right, like this is a n minus here, but here this becomes n plus, like huge doping is there, this becomes a n-type region, right, called the n channel. Since the drain is positive relative to the source, electrons flow from source to drain. So drain is positive relative to the source, so due to this n channel, right, all the electrons are getting attracted to this drain as well. Okay, now consequently current flows from drain to source. Electron flow path is from n plus source, like from this positive source to n channel. Like from this the electrons go to this channel, then they come to this drain, to this like drift layer, and then they come to this drain, right? This is n minus drain, this is n minus. Just hold on. N minus drift, okay, to N plus drain. So this is basically the flow of electron, and like the channel is formed and the current flows. The device has no PN junction here. Like during the flow of electrons, right? During the flow of current, the current flow path doesn't have any PN junction. So the flow of electrons, the electron flow path, the electron, hence this is a majority charge carrier device. Flow path has no PN junction. Has no PN junction, making it a majority carrier device, unipolar device, also known as unipolar because only one type of charge is flowing. Also, we can only block one polarity of voltage, forward voltage. Reverse voltage, we can only block very minimal amount of voltage, which we ignore. Due to the body diode, it conducts in the reverse direction. Okay, so the minimum gate voltage required to create the N channel is called the threshold voltage. This you have been taught in the MOS physics part. Okay, so like this is the IV characteristics of a MOSFET. Like there, I don't think you have mentioned body diode. Just what happens is, due to this body diode, right, the current can flow in the reverse direction as well. So that's why this is a bidirectional. So due to this body diode, right, current can flow in the reverse direction. This is the IV characteristics of a MOSFET. So this is the VGS and this is the current I, right? So as VGS keeps on increasing, the current I will also keep on increasing because the N channel will be more stronger and more electrons will be present here and more current flow will be there. Okay, so that is the VGS, and this is the current flow in the reverse direction is due to the body diode. So it generally blocks very lower amount of voltage. Okay, so this is the practical characteristics and this is the ideal characteristics. If I am on the x-axis, this is off. Okay, on the right hand side of the x-axis. If this is on the y-axis, on the positive side, this is on, and this is on, this is working in the reverse conduction mode, right, when the body diode is on. So in this region, the body diode is on, or I can say the body diode is forward bias. Body diode is forward bias. Okay, so like a few key points about a power MOSFET is it has more conduction loss compared to BJT. Why? Due to conductivity modulation, as it is a majority charge carrier device. Basically here, right, there is no conductivity modulation here. There is no conductivity modulation. There is no PN junction, so there is no conductivity modulation as well. So BJT had the conductivity modulation which had lower power loss as the R1 was reducing. Here R1 doesn't reduce due to, I should say, due to no conductivity modulation. Okay, it provides minimum switching loss in comparison to any other power electronic devices. Why it has minimum switching loss? Because basically the gate current is 0, right? Like turn this on, gate current is 0, so no, like it takes no current, so like the power loss due to this gate terminal is 0, and simply this N channel is formed and power flows through this, right? There is no junction, that's why it has minimum switching loss. So if there is no junction, there is no charge storage, so hence there is no like reverse recovery charge or reverse recovery time. So this also takes minimum time as well. Okay, minimum switching loss, and also it has like high switching frequency. You can use it in very high switching frequency applications. It is free from second breakdown problem. Basically it doesn't have any that thermal runaway type of thing, right? It doesn't have that. Let's do a question in this. Which of the, just hold on a second, this is okay, right? Yeah, it's okay. Which of the following statements is /r correct regarding power MOSFETs? The gate circuit impedance of MOSFET is higher than that of a BJT. Is it true? The gate circuit impedance of a MOSFET is higher than that of a BJT. Like what is the gate equivalent of of MOSFET in BJT? It is the base terminal, right? So yeah, some current flows in the base terminal and we apply some voltage, but in MOSFET, right, no current flows. So the input impedance is infinity. Input impedance is infinity. Okay. Next is the gate circuit impedance of MOSFET is lower than that of a BJT. The gate circuit impedance of a MOSFET is low. No, we've already told this is correct, so this is not the correct answer. The MOSFET has higher switching losses than that of a BJT. The MOSFET has higher switching losses than that of a BJT. No, right? MOSFET doesn't have any switching loss because the gate current is 0 and there is no charge carrier storage. It is a majority carrier device, charge carrier device, so it doesn't have any switching losses. The MOSFET has lower switching losses than that of a BJT. True, because it is a majority charge carrier device. It is a charge carrier device. Okay, so basically the turn on time, turn off time, all these are low, and our P switching, right? So T on, as there is no charge storage, T on is low, T off is low. Okay, hence power switching, as we have derived it, is proportional to direct T on plus T off, right? If you remember correctly, like this is the small T on and small T on, right? This is not the capital T on and capital T off, else you will get confused with the notation. Small T on and T off. So it is proportional to this. Hence what we can say is this has been reduced, so hence P switching also will be reduced, right? Power loss due to switching also will be reduced, so option 4 and 1 will be correct. Okay, so these two are correct. Let's go to the next question. Choose the correct statements. Both MOSFET and BJT are voltage controlled devices. So is it correct? No, MOSFET is a voltage controlled device, but BJT is a current controlled device. We control with the base current, so this is not the correct answer. Both MOSFET and BJT are current controlled device. Again, not true. MOSFET is a voltage controlled device, whereas BJT is a current controlled device, which is correct. MOSFET is a current control device, whereas BJT is a voltage control device, which is wrong. Okay, these are just control device, whereas BJT is a voltage control device. So this will be, yeah, this will be this, right? So like these are few basic questions which can come, but most probably this won't come because this comes in the analogs electronics section only. Just try to take few theoretical questions. That's why. So next will be the IGBT. This is the newer version. Okay, and this is the like it takes both worlds. It takes good things from both worlds, from the MOSFET as well, from the BJT as well. So there might be, like, it will try to take all the good things, but one issue may happen that it might take up some bad things as well. So that is the issue with IGBT. IGBT is basically what? IGBT is insulated gate bipolar transistor. Okay, so it is an insulated gate bipolar transistor, and IGBT symbol is something like this. Okay, IGBT symbol is something like this, and its construction is basically, if we take a MOSFET and if we take a BJT, and it's literally that only, and it will make a IGBT. IGBT has gate terminal, it has emitter, and it has collector. So what is the good thing about gate? Terminal doesn't have any current through it, right? That is the good thing. So it took the good thing from MOSFET, and collector and emitter it took from the BJT. Okay, so we'll understand about the construction. The construction is very complicated, so we don't have to understand about it in that much of a detail. Just we have to understand the high level things. So due to presence of the drift layer, conduction modulation occurs here. So here, like, there are PN junctions as well, right? Here there are PN junctions, so we have to take care of that as well, right? So previously there wasn't any PN junctions. Here, like, there are so many junctions: J1, J2, J3, J3, J2, J1. Okay, all these junctions are there. Okay, so I will not go into the working of IGBT because that will be just a waste of time. Okay, and they will not ask that. So what they will ask is few theoretical points about IGBT that I will talk about here. Okay, so like you can see there are PN junctions here, and as like what is happening, the current flow is from P, then it is going to N, right? There is a junction, so that's why there will be like conduction modulation will happen, and due to conduction modulation the conduction loss will be less. Okay, BJT has lower conduction loss but longer switching time. So although the conduction loss is lower but not lower than BJT. Okay, but what is happening here, it takes the good thing from MOSFET that it has lower switching time, so it will have less reverse recovery time. Okay, IGBT will have less reverse recovery time than BJT. MOSFET has faster switching but higher conduction loss. Why is the higher conduction loss? As conduction modulation is not present in MOSFET. That's why IGBT combines advantages of both BJT and MOSFET. Okay, obviously few disadvantages also come. The structure of IGBT is similar to MOSFET, but the N plus drain is replaced by P plus collector. So here, right, previously it was N plus, right? This was N plus. Now it has been replaced with P plus. So there is a PN junction through which the current flows. So that is one of the issue. So yeah, that is basically what is the difference in the IGBT construction and the MOSFET construction. Almost similar to MOSFET, just the N plus region has been replaced with P plus region. So source becomes emitter, drain becomes collector. When a positive voltage is applied to the gate, an electric field forms N channel below the gate terminal. So just similar like this MOSFET only. So a N channel has been formed here below the gate terminal, allowing current to flow through a PN junction. So instead of previously it was totally flowing, current was totally flowing through this N channel only, through this N minus and N plus. Now there is a PN junction. This is P, right? So there is a PN junction. So current is flowing through the PN junction. So there is a junction. So it will be a minority carrier device now. Okay. So there is a junction. Just hold on. Yeah, so I will like the direction of current also they have shown, right? This is the direction of current. It will flow through PN junction. Okay. Next, the P plus collector injects. Oh, just hold on. This is allowing current to flow PN junction. The P plus collector injects holes and N plus emitter injects electrons into the drift layer, increasing the conductivity and reducing R on. Basically, conductivity modulation happens in this drift layer and it reduces the R on due to silicon oxide layer present in the gate. Hence, gate current is 0. We don't apply negative voltage to IGBT as it may get damaged. Again, like it has a problem of getting damaged if we apply a negative voltage. Okay, so we don't apply negative voltage, so we don't work in the reverse direction of IGBT. Okay, like these are the IV characteristics of IGBT. We only use the positive voltage, we don't use the negative voltage. Okay, so yeah, these are the IV characteristics, and like this is almost similar to BJT, but just a bit different is the active and cutoff region. All these things, that is saturation region. This characteristic is similar to what BJT, right? So this you have to take care of. Yeah, this is VGE, right? This is not. This is VGE. This is IC. Okay, and this will be also VGE, I believe. Yeah, this is VGS anyway, so it's fine. So yeah, that is the VI characteristics of IGBT. Now let's understand the latch-up problem in IGBT. To understand the latch-up problem, you need to understand ACR. So what I will recommend is, you can skip this portion for now, the latch-up problem, and then I will come back to it. Write it down in your notebook to come back to it after you have studied about ACR. Okay, so like the basic of ACR, if you know, then you can continue to watch, or you can skip this portion and then come back exactly here after you have studied ACR, because you will not be able to understand few things here. So what is happening? A parasitic SCR forms within the IGBT with its 4-layer collector, drift, body and emitter. Why? Because a PN type of structure is forming, and in SCR exactly this type of structure is there, right? So a parasitic SCR is formed in the IGBT. So what happens is that when the collector current flows, basically this collector current, when this current flows right from here to here, when this collector current flows, it causes a voltage drop across the body region, which acts as the gate of the SCR. So this is the body region, right? And if this collector current flows, a drop has been occurred across this body region, and if the drop is higher, so it acts as a triggering signal to this SCR, and this SCR turns on. What happens if this SCR turns on? If this SCR turns on, if the collector current IC is high, the voltage drop across the body resistance will be increased, and which can trigger the parasitic SCR. Once the SCR conducts, the gate terminal loses control. The gate terminal loses its control, right? So basically, I don't have the control anymore. So if I remove the gate voltage, this will still be on. So it latched up. Okay, this latches on to the on state. I cannot turn off the device. This becomes a semi-controlled switch. Okay, this, due to this latch-up problem, this becomes a semi-controlled switch. Latches to on state. So even if I remove the gate supply, right? Even if I remove the gate supply, this will still be on. So this becomes semi-controlled. Semi-controlled. Okay, just hold on. Just hold on. Controlled. I cannot control the switch with the help just hold on. With the help of gate terminal. Okay, So that's why this becomes semi-controlled, because this latches on as the parasitic SCR is on and current will flow through this parasitic SCR. It doesn't need this gate terminal anymore. So manufacturers specify a limit on the collector current to avoid turning on the parasitic SCR. So this is specified, like this has a limit on the forward current, right? This has a limit on the forward current. We cannot flow very high amount of forward current. So that is the limit. Now why IGBT is faster than BJT? So IGBT has only one PN junction in its current path. So this is the PN junction, right? If you observe, this is the P plus and that's it, right? This is the junction, PN junction. But BJT has two junctions. BJT has two. That's why obviously IGBT will be faster because there will be less charge storage. The PN junctions reduce the speed due to reverse recovery. As I just explained, the gate in IGBT is insulated as there is no gate current. It is insulated, so no charges are injected from the gate, hence there is low switching loss. Okay, so no charges need to be removed when turning off. But unlike in BJT, where charges need to be removed from the base. Okay, charges need to be removed from the base, right? So it is important to understand these things as well, right? So that's why BJT is IGBT is faster than BJT. Now there are a few key points about IGBT that you should know that can come in examination, different state level examination, and also gate can ask a bit about theory in the theoretical points about IGBT. First of all, it is a voltage control device because it is inherited from MOSFET. I control the gate terminal voltage, right? It is a unidirectional device because current can only flow in one direction. Current cannot flow in two directions, unlike MOSFET, right? This is due to BJT, right? It has on-state characteristics like BJT, and its drive circuit, that is basically the control drive, or I can say the control circuit, right? Control circuit is almost like the MOSFET, right? Next, it is a minority charge carrier device because there is a PN junction. Obviously, it will be a minority charge carrier device. It has high conduction loss in comparison to BJT, but lower compared to any other devices. So why high conduction why high conduction loss compared to BJT? Because BJT has two PN junctions and it has better conduction modulation than this, but this has also conductivity modulation, right? But MOSFET doesn't have. So MOSFET has more conduction loss than this. So this comes in the middle. IGBT comes in the middle of power MOSFET and the BJT in terms of conduction loss. BJT has the lowest conduction loss. IGBT has a bit more conduction loss than BJT, and MOSFET has the highest conduction loss. Now it has positive temperature coefficient during switching. So this you should know that it has positive temperature coefficient during switching. Like this is just a theoretical point. That's it, right? It is free from secondary breakdown problem, so it doesn't have the same thermal runaway problem like BJT. The on-state characteristics, the drive or control circuit of IGBT is similar to MOSFET, and the on-state characteristics of IGBT is similar to that of a BJT. Also, the IGBTs have replaced BJTs in many applications because IGBTs are more preferred. So, in this one slide, right, I have totally explained the core differences between power BJT, power MOSFET, and IGBT. So, you can put this in your short notes, okay, so that you revise this daily, right? This is very important. And you revise this daily so that if they ask some theoretical question, you can answer from this. So, power BJT is a minority charge carrier device. Power MOSFET is a majority charge carrier device. IGBT is a minority charge carrier device. Like power BJT and IGBT will have same charge carrier and all those things. Few things will be different. Now it is a current control. This is a voltage control. The control circuitry will be same for IGBT and MOSFET. Okay, so it is also a voltage control. It has low on-state voltage drop. This has higher on-state voltage drop due to no presence of conductivity modulation. It has also low on-state voltage drop due to presence of conductivity modulation. It has lower conduction loss. This is lower, and this R1 is also lower. This is also lower, but this is higher. Higher switching loss because this has PN junction, right? That's why there is high switching loss, because we have to deplete the charges, the stored charges which were there when the device was on. This has lower switching loss because the gate current is 0 and we don't have to deplete any charges. We don't have any reverse recovery charge. So that's why it has lower. This is also lower because it has only one junction. That's why the charges needed to deplete is lower in number than this BJT, right? This is negative temperature coefficient. This is positive. This is also positive temperature coefficient. So if temperature increases, current will decrease. Why? As this is a positive temperature coefficient, right? If temperature increases, the resistance also increases. If the resistance increases, the conductivity decreases. If the conductivity decreases, current will decrease. Hence, this is a positive temperature coefficient. This is the same reason. All these are during switching obviously. And this is negative temperature coefficient because this has thermal runaway. So if the temperature increases, current will increase, conductivity will increase, current will increase, and if the current increases, temperature will again increase, right? So that is the loop basically. So it has secondary breakdown problem, as I explained. No secondary breakdown problem, no secondary breakdown problem. Parallel operation is not advisable due to this secondary breakdown problem, right? The reason is due to this secondary breakdown problem, parallel operation is not advisable. What do you mean by parallel operation? We'll use few switches in parallel at the end of SCR. After studying all the switches, we'll use those in parallel. There we'll understand what do you mean by parallel operation. Okay, and you can study the IGBT again, just the latch up part once we finish the SCR part. Okay, parallel operation is possible. Parallel operation is possible. Now, this rating has higher rating, but the frequency is much lower, right? Switching frequency is much lower. The rating is medium for power MOSFET, and switching frequency is much higher. It will have the highest switching frequency, but the rating will be a bit lower. Okay, but it can, like this IGBT is medium rated. Okay, and its switching frequency is also medium, right? So this is used where I need medium specification. So all these three switches have its own application. It just depends which one I need. Okay, this is the main comparison between power BJT, power MOSFET, and IGBT. Next, which of the following statements is/are correct regarding the latch-up of IGBT? A large current flows through the IGBT, which can lead to excessive power dissipation. So, true, right? As like what happens is, if my IC is very high, right? If my IC is very high, large current will flow and the device will latch up. When latch up happens, obviously IC is very high. IC is very high. So this is true. It can cause significant heating, potentially damaging or destroying the IGBT. Yes, right? If IC is very high, it can obviously damage the IGBT because I am the current is flowing more than the spec limit which I have specified for the device. So it can cause heat damage. The device turns off safely. No, right? The device doesn't turn off. Device is on always. Okay. The gate control loses its ability to turn off the IGBT, making the device uncontrollable, which is true, right? So we don't have the control over the IGBT anymore, because even if I remove the gate supply, as the parasitic SCR is on, so IGBT will anyways be on, right? It doesn't matter regarding the gate. We lose the control for the gate terminals. Okay. Next is, what determines the voltage blocking capability of an IGBT? What determines the voltage blocking capability of an IGBT? So basically, does injection layer determines body layer or metal used for the contacts, or drift layer? So again, right, blocking capability is always determined by the drift layer, because we implement the drift layer only to block the voltage. That's it, right? We implement the drift layer to block the voltage, high reverse voltage. So obviously, drift layer is responsible for the high voltage blocking capability. In an IGBT, what is the P plus layer connected to terminal cord? So here, like this is just a theoretical question. So here, right, what happens is it injects holes, right? This P plus layer injects holes. That's why this is known as the inject layer. That's it, right? Drift layer is N-1. Collector layer is collector. Isn't connected to collector layer. It is just the collector terminal, right? Body layer is here, right? Body region is here. So that is not true. So it will be inject layer. This is just a theoretical point that you should know, right? So as we inject holes, that's why this is known as the injection layer. Okay, so basically that's it about IGBT. Like mainly this is a theoretical topic. We will understand, like I told you, the characteristics and all those things about IGBT, BJT, power MOSFET. Just the comparison part is very important. Just keep that in mind. That is the most important part. From that the questions may come, right? And obviously we'll apply all these switches after we finish studying about all the switches. Next we'll start with SCR, and it is a very, very important topic, and maximum chances are there that questions in the first chapter will come from SCR only. So you have to study SCR in a fully concentrated manner. Thank you for watching, and I will see you in the next lecture.